I welcome you to free Jamb Mark series for Jamb UTME 2026. Do not forget to make your own notes. Momentarily pause the video and write what you hear and what you understand during this lecture. At this time, I am distributing free marks for Jamb UTME 2026. Do not forget to obey the lecture protocol by enabling full screen view in your device by tapping on the icon located at this place that I'm hovering my mouse. Without wasting much of our time, let's head straight into the Jamb repeated question. Jamb repeated question. Which of the following elements is the most reactive? Very, very common in Jamb. Always repeated every year in Jamb UTME. Which of the following elements is the most reactive? Which of the following elements is most reactive? A. Fluorine. B. Oxygen. C. Chlorine. D. Nitrogen. What's the answer? Let's find out. Of Jamb's question style in this same topic, in the same subject. The first reads, which of the following elements is the second most reactive? They can ask you second most reactive. Which of the following elements is the least reactive? They can also ask you least reactive. The next, which of the following elements is the least stable? They can also ask you this question as least stable. The final here is, which of the following elements is the most unstable? They can also set the question asking, what's the most unstable element? And so on and so forth. So let's understand the concept of this question and how to answer it. Valence electrons. We have to know what valence electron is. What is a valence electron? Valence electron is the number of electrons in the outermost shell of the atom of an element. The number of electrons in the outermost shell of the atom of an element. That's the valence electron. How many electrons is found in the outermost shell of the atom of an element? How many? That's the valence electron. There are some terms you have to have at the tip of your mind. You need these terms. You need to know them. The first term here is the starting point. And what is the starting point? This is the first electron of a shell's capacity. Each of the shell of an atom has electron capacity. The capacity of electron that it can hold. The amount of electron that it can accommodate at a given energy level. That is the electron capacity of the shell. So starting point is the first electron of a shell's capacity. So the first electron in that shell capacity is the starting point. It is the starting point of the electron capacity of the shell. For example, if maximum shell capacity is 8, that's the second shell. The maximum shell capacity of the second shell is 8. Okay, so if maximum shell capacity is 8, the starting point is 1. So the starting point is 1. The first electron of the shell's capacity. That's the starting point. Another term you have to have at the tip of your mind, you have to know it by heart, is the central point. The central point. What is the central point? This is the middle electron or electrons of a shell's capacity. The middle electron or electrons of a shell capacity. It is the middle point of the electron capacity of the shell. The middle point of the electron capacity of the shell. For example, if maximum shell capacity is 8, that's 8 is the maximum shell capacity of the second shell, okay? The center point is 4 and 5. So what is the center point of 8? 4 and 5 are both the center points of 8. So that's it. The middle point of the shell capacity. The middle point. If it's 8, the center point is 4 and 5. That's that for that. Let's look at the final term you have to memorize and know by heart. The ending point. And what is the ending point? This is the last electron of a shell's capacity. It is the ending point of the electron capacity of the shell. The last electron of the shell capacity. It is the what? The ending point of the electron capacity of the shell. The ending point is the ending point. So for example, if maximum shell capacity is 8, the ending point is 8. That's that for that. The ending point is what? Is 8. So the three terms to note and to have by heart is the starting point, the central point, and the ending point. Very, very important because we are going to use it very soon. Moving on. Maximum electron capacity. What is the maximum electron capacity? This is the highest number of electron each shell can accommodate. The highest number of electron each shell can accommodate. They go according to the shell. For example, first shell, the maximum electron that it can accommodate is 2 electrons. Maximum capacity. The second shell, the maximum electron that it can accommodate at an energy level is 8 electrons. Maximum capacity. The third shell, the maximum electron that it can accommodate is 18 electrons. The maximum capacity is 18 electrons. Then the fourth shell, the maximum electron that it can accommodate is 32 electrons. That is the maximum capacity. Hope you are making notes. Hope you are pausing the video momentarily and making your own notes because this note is what you are going to revise to master this free mark. Do not miss this opportunity to ace your Jamb UTME 2026. How to answer it? How do we answer this Jamb repeated question? Most reactive element, most unstable, the second most reactive, the least reactive, and so on and so forth. How do we answer this question? First of all, the first thing you need to do in any exam you are taking is, number 1, read and understand the instructions first. Read and understand the instructions first. This is the foundation of answering questions in exam. Okay, this is the foundation of answering questions in exams. If you miss it here, reading and understanding instruction, you are going to fail. You've missed it all. So the instruction is number 1. Read, understand, and obey instruction. Then number 2, determine the atomic number of the element. What is the atomic number of the element? You have to determine that. Determine the atomic number of the element. Then number 3, draw the orbital diagram of each of the elements. Draw the orbital diagram of each of the elements. Ensure you are taking notes. Ensure you are pausing the video and making notes. Then number 4, the valence electron or electrons determines reactivity / stability. So the valence electron of the elements determines its reactivity or stability, or it determines its reactivity and unreactivity. It determines the reactivity and stability of the element. So what do you do? What's the fifth? The fifth and final technique is what? Pick the correct option. You are good to go. You've earned the free mark. So let's illustrate this in a real sense from 1 to 5. For example, we are taking fluorine as one of the elements provided in the option. Okay, so fluorine, first of all, we have to read the instruction. We have read and understood the instruction. So we are trying to follow the instruction. Okay, so the instruction says which of the elements is the most reactive. So we want to find the most reactive element. The second thing to do is what? Find the atomic number of the element, which is what? 9. The atomic number of fluorine is 9. The atomic number of fluorine is 9. So after figuring out the atomic number of the elements, what do we do next? We draw the orbital diagram or the shell diagram of the elements. Let's learn how to draw the orbital or shell diagram together. The first thing you have to do when drawing the shell diagram, ensure you are making notes. Ensure you are making notes. Ensure you are writing. Pause the video and take notes. The first thing to do, first step of drawing the shell diagram is what? Draw the first shell. Draw a circle. The first shell, just draw a circle, okay? Draw a circle, 1 circle, the first shell. After drawing the first circle, what do you do next? The second is what? Put the electrons according to the capacity. That was why we treated the capacity first, indicating each of the shell, the 4 shells and the maximum electron that each of them can accommodate. So this is the first shell. How many electrons can the first shell accommodate? We just treated that is what? 2 electron, maximum capacity. So we are going to do what? We put the 2 electron in the first shell that we just drew. And moving on to the third step. The third step of drawing the orbital diagram is draw the second shell. We just drew the second circle. You can see the second circle here. We drew the second circle. So that's that. After drawing the second shell, let's look at the fourth step of drawing the orbital diagram. The first step says put the electrons according to the capacity. That's how you are going to continue drawing the shells and putting the electron according to the capacity, the maximum electron capacity. So what is the maximum electron capacity of the second shell? Is 8. So 8 is the maximum electron capacity of the second shell. So how many electrons did we put in the second shell? 1, 2, 3, 4, 5, 6, 7, 8. So that's correct. So we have drew the second shell and inserted the maximum electron capacity, which is 8. Moving on, continue in that sequence until you exhaust the atomic number of the element. So as you are drawing the orbital diagram or the shell diagram, you are calculating, you are counting the atomic number of the element and ensuring that it matches the atomic number of the element. Okay, so the atomic number of fluorine is 9. So since atomic number of fluorine equals 9, let's go back to the orbital diagram that we just drew. Okay, this is the orbital diagram we just drew. What did you notice here? Number of electrons have surpassed the atomic number of fluorine, which is 9. And what did we do next? We removed 1 electron, which is this. We removed 1 electron. So this is the orbital diagram of fluorine. This is the orbital diagram of fluorine. So if you count the electrons present here, you are going to get 9. Let's count it shell by shell. Let's count the second shell first. 1, 2, 3, 4, 5, 6, 7. Let's count the first shell next. 8, 9. So we have 9 electrons in the atom of fluorine. So we now know the outermost shell. So the second shell we have here is the outermost shell of fluorine. When you look at this orbital diagram, we now have 7 valence electrons. Remember, the valence electron is the amount of electron in the outermost shell of the atom of an element. So the amount of electron in the outermost shell of an atom is the valence electron. So let's count the amount of electrons we have in the outermost shell of the fluorine atomic diagram that we just drew. Let's count together. The outermost shell is obviously the second shell. So let's count. 1, 2, 3, 4, 5, 6, 7. So we have gotten the valence electron. That's the amount of valence electron fluorine has. Moving on, this is how you are going to draw the orbital diagram for the whole elements in the option. So all the elements provided in the option, for you to know the one that is the most reactive or the least reactive, this is how you are going to continue drawing all the orbital diagram of all the elements in the option in order to figure out the respective valence electron, because it's that valence electron that you are going to use to point out the reactivity or stability of the element. But the big question is, do you have such time in an exam condition? Do you have such time in an exam condition to be drawing all the orbital diagram of all the elements provided in the option? You don't have that time in your Jamb UTME. So here comes the shortcut. I'm a good guy. I will always give you the shortcut. I will always give you the best. So I'm a good guy. So ensure you are writing down, ensure you are pausing the video and taking this down. Make your own notes. So here is the shortcut. Since you now know the maximum electron capacity of each shell, you know the maximum electron capacity of each of the shells. You know them by heart. So you know the atomic number of the elements too. You know the maximum electron capacity of each shell, the 4 shells, which is the first shell is 2, second shell is 8, third shell 18, fourth shell 32. Those are the maximum electron capacity of each shells. So you know that, and you have figured out the atomic number of the elements too. So what do you do next? The maximum electron capacity is represented as 2, 8, 18, 32. That's it. First shell is 2, second shell is 8, third shell is 18, fourth shell is 32. So this is how you are going to write it: 2, 8, 18, 32. So these are for the 4 shells. Okay, for the 4 shells. So moving on, let's look at what we are going to do next. So for example, let's say atomic number of oxygen equals 8. So maximum electron capacity of the normal 4 shell, the general maximum electron capacity is 2, 8, 18, 32. So what do? We subtract the first shell capacity from the atomic number. So the first shell capacity, 2, you will subtract it from the atomic number of the elements. The atomic number of oxygen is 8. So 8 minus 2 is equal to what? 6. Let's look at the next step. So after subtracting the first electron capacity from the atomic number of the element, what do you do next? If the remainder is greater or equal to the next shell capacity, remember the first shell capacity is 2, the next shell capacity is 8. But if the remainder is greater or equal to the next shell capacity, what do? You subtract it. But if it's lesser, the remainder is the valence electron. You've just discovered the valence electron of the element. If the remainder is lesser than the next electron capacity, that is the valence electron. That remainder becomes the valence electron of the element. So 8 minus 2 is equal to what? 6. In the above, the next shell capacity is 8. General shell capacity is 8. So the question is 18 greater than the remainder we have here, which is 6? Because the next shell capacity is greater than our remainder 6, meaning that 6 is the valence electron of the element, which is oxygen. Element with atomic number 8, 6 is the valence electron of the element. Thus, the valence electron of oxygen is 6. So, other than drawing orbital diagram, this is the shortcut, the easiest way to get the valence electron of the element. Moving on, I want you to note something very important. Note, if the remainder is equal to the next shell capacity, maybe your remainder now is now equal to the next shell capacity, such element is completely stable, cannot take part in a chemical reaction. These elements are called what in the periodic table? They are called the noble gases, which have a completely filled outermost shell. So they are stable, they can't take part in a chemical reaction. Why? Because they don't have electrons to donate and they can't receive electrons because their various outermost shells have been filled with electrons. So they can't take part in a chemical reaction. They can't take part in redox reaction. They can't donate electron. They can't receive electrons. Moving on. How to use valence electron to determine reactivity/unreactivity. So having figured out the valence electron of the element, the next step is to determine the reactivity and unreactivity of the element using the valence electron. It determines reactivity and unreactivity, or unstability and stability of an element. So the valence electron of an element determines the reactivity and unreactivity of an element, or the stability and instability of that element. The closer the valence electron to the starting and central point, the higher the reactivity and instability of the element. So when an element is unstable, that shows that the element is reactive, highly reactive, ready to donate or accept electron. And how does the valence electron determines this reactivity? The valence electrons determines it by the starting and the central point. If the valence electron is closer to the starting and the central point, remember the starting point in electron capacity. Okay, the first electron in an electron capacity of a shell is the starting point. So the central point is the electron located in the middle of the electron shell capacity. Okay, so that's the central point. So if the valence electron is closer to the starting point and the central point, the higher the reactivity of the element, the higher the unstability of such element, closer to the starting point or the starting of the electron capacity and the central point of the electron capacity. The second law states that the farther the valence electron to the ending point, the lower the reactivity and unstability of the element. So when the valence electron is farther away, is far from the ending point, you know what the ending point is? The last electron in the maximum electron capacity of a shell. So that's ending point. So when the valence electron is farther away from this ending point, for example, the ending point of the shell is 9 and the valence electron is 4, that shows that this element is not reactive. It shows that the element is not reactive. So the farther the valence electron from the ending point, the lower the reactivity. The closer the valence electron to the ending point, the higher the reactivity of the element. So let's go back to the Jamb repeated question and apply what we just learned. The question reads, which of the following elements is the most reactive? A. Fluorine, B. Oxygen, C. Chlorine, D. Nitrogen. When you do the orbital diagram, first of all, find all the atomic numbers. We know the instruction already, so look for the atomic number. So the atomic number of nitrogen is 7. So when you do the normal electron capacity, the general electron capacity 2, 8, 18, 32, then you start minusing each of the electron capacity from the atomic number. First of all, 7, we minus 2 from 7, we get 5. So the next electron capacity we have there is 8. Can we subtract 8 from 5? No. So that tells you that the valence electron of nitrogen is 5. Can you see how fast I was able to figure the valence electron of nitrogen? So that's how you are going to do it for the rest of the elements. Very fast, very easy. When you are done figuring out the valence electron of all the elements, you use the laws of reactivity and unreactivity to confirm your answers, okay? Confirm your answer with reactivity and unreactivity. So the element here, fluorine, we already know the valence electron of oxygen. We just did that and we got 6. So the valence electron of fluorine is what? We just did that. We also did the valence electron of fluorine. And the valence electron of fluorine is 9. So since the valence electron of fluorine is 9, the valence electron of oxygen is 6, the valence electron of nitrogen is 5. And all the elements here did not exceed 2 shells. That's the first and the second shell. We didn't draw more than 2 shells for each of the elements here. For each of the elements here, didn't draw more than 2 shells. So we are banking on the second electron capacity, which is 8. That's what we are going to use to interpret the law. Okay, so let's go back to the law. It says the closer the valence electron to the starting and central point, the higher the reactivity or stability of the element. So remember what the starting and central point is. The starting point is the first electron. The central point is the center electron. Remember, is the electron of the electron capacity of the particular shell that the element orbital diagram stops in. So like we said, all the elements ended in the second shell. So no need, we are going to use the second shell as the base, which is 8. Okay, the maximum electron capacity of second shell is 8. The first element we did is what? Nitrogen. And the valence electron of nitrogen is 5. So 5, it says the closer to the starting point. The starting point is 1. Central point of 8 is what? 4 and 5. So 5 is exactly the central point of the maximum electron capacity, which is 8. So this element is reactive, but not so reactive. So let's look at the next valence electron of the next element we got, which is oxygen. And oxygen is actually 6. So the valence electron of oxygen is 6. So using this, basing on this, the closer the valence electron to the starting point and the central point, the higher the reactivity or stability of the element. So the central point is 4 and 5, while the starting point is 1. Is 6 closer to 4 and 5? Yes, 6 is closer to 4 and 5. The starting point is 1. 6 is not close to 1, but 6 is closer to 4 and 5. After 5, 6. Very close to 4 and 5. So that tells you that this element is very reactive. It's more reactive than the former one, which is nitrogen. So the valence electron of fluorine is 7. Based on this first law we have here, it says the closer the valence electron to the starting and central point, the higher the reactivity. So is 7 closer to the starting point? Remember the second shell, that's what we are using, the maximum electron capacity of the second shell. Is 7 closer to the starting point, which is 1? No. So it's farther away from the starting point. So let's look at the central point. Is 7 closer to the central point, which is 4 and 5? So 7 is very close to the central point. And the central point is 4 and 5, and we have 7. But the law states here that the farther the valence electron to the ending point, the lower the reactivity or stability of such elements. It means that when it's close to the ending point, the higher the reactivity. So when is farther away from the ending point, the lower the reactivity. But when it's closer to the ending point, the higher the reactivity. That makes fluorine the best candidate. But because fluorine valence electron is 7 and the ending point is 8. So the closer the valence electron to the ending point, which is 8, the higher the reactivity of the element. So fluorine reacts way more than oxygen, chlorine, and nitrogen. So under these options, if you are looking at the next most reactive here is chlorine, and the next most reactive here is oxygen, followed by nitrogen. Oxygen is wrong according to the instruction in the question. Chlorine is wrong. Not that they are not reactive, they are reactive, but the question reads most reactive. Nitrogen is also wrong. Or for the correct option, which is fluorine, the most reactive element among the listed. Fluorine is the most electronegative element on Earth. So fluorine, very, very reactive, very, very reactive, highly electronegative. So let's look at the second Jamb repeated question. Question 2 reads, which of the following metals is the most reactive? Which of the following metals is most reactive? Take note of the key word here, metals. Which of the following metals is most reactive? A. Potassium. B. Sodium. C. Calcium. D. Magnesium. Which of the following metals is the most reactive? Let's find out the answer. So, other shortcuts. There is also another shortcut, especially when it involves metals, okay? So, another shortcut that works only for metals is getting familiar with the activity series. Okay, the activity series of metal. Activity increases as we ascend the activity series, while reactivity decreases as we descend the activity series. So the reactivities of metals rises as we ascend the activity series. So reactive, more reactive, more reactive, more reactive, more reactive, more reactive. As you ascend, reactivity increases. Okay, so the topmost is the most reactive, while the lowest is the least reactive. But reactivity decreases as you descend the activity series. So as you are going down, reactive, less reactive, less reactive, less reactive, less reactive, and so on. As you descend the activity series, the trend is the reactivity of elements decreases, but it increases as you ascend. So just have it in your mind that as you go up, reactivity goes up. As you come down, reactivity decreases. So let's look at the activity series of metals. The activity series of metals, that's what you can see on the screen. Okay, the first we have here is potassium, which is the most reactive metal in the activity series. The second is sodium, calcium, magnesium, aluminium, carbon. Okay, carbon is not a metal, okay, but carbon is among the activity series. You have zinc, you have iron, you have tin, you have lead, you have hydrogen. Hydrogen is also not a metal, but it's part of the activity series because of its ions, okay, because it's positively charged. You have copper, you have silver, and gold. So this is the activity series. You can see as it goes down, you can see the arrow. As it goes down, take note of the color codings. As it goes down, least reactive. The reactivity of the element reduces as it goes down. That's the trend, okay? As it decreases, as you go down this activity series like this, the reactivity decreases. So potassium is more reactive than sodium. Sodium is more reactive than calcium. Calcium is more reactive than magnesium as you go down. So when you are ascending, reactivity increases as you ascend, as you go up. So this one, AU, is gold, is least reactive than silver. So silver is more reactive than gold. Copper is more reactive than silver. Hydrogen is more reactive than copper. Lead is more reactive than hydrogen. Tin is more reactive than lead. Iron is more reactive than tin. Zinc is more reactive than iron. Until you get to the topmost, which is potassium, the most reactive. So that's that for the activity series. So how do you use the activity series to figure out the most reactive and least reactive metal? You just have to know the activity series by heart. You have potassium, you have sodium, you have calcium, you have magnesium, you have aluminium, and so on and so forth. You have to know the position of each of the elements in the activity series. This is also another alternative if you don't want to be drawing orbital diagram or you don't want to be cracking your head with orbital diagram. So if you can memorize the activity series of metals, you can easily figure out the most reactive metal or the least reactive metal, but you can't use this for non-metals. That's the limitation of this activity series in an exam condition. You can't use it for non-metals. So let's quickly go back to the question. The question reads, which of the following metals is the most reactive? A. Potassium. B. Sodium. C. Calcium. D. Magnesium. What's the answer according to the activity series? The correct option is A. Potassium. Potassium is the most reactive and it is the topmost in the activity series. You can also use the orbital diagram to answer this question. When you draw the orbital diagram of potassium, for example, following the maximum electron capacity, first of all, the atomic number of potassium is 19. So when you do that, you are going to, the normal maximum electron capacity of the 4 shells are 2, 8, 18, 32. So the atomic number of potassium is 19. 19 minus 2 is what? 17. So you do the next one. 17 minus 8, you have 9. So you go to the third shell, which is 18. Can you minus 18 from 9? No. So 9 is the valence electron of potassium. So following the rule of determining the reactivity and unreactivity of the element, how do you determine it? Remember the starting and the central point. The closer the valence electron to the starting and central point, the more reactive the element or the atom is. So remember, the electron capacity of the third shell, we got to the third shell, the electron capacity is 18. We are going to use 18 to calculate the starting point. The starting point of 18 is what? 1. The central point of 18 is what? 9 and 10. Okay, so that's the central point of 18. And it says the closer it is to the central point, the more reactive the element is. So is the valence electron 9 not very close to 9 and 10? Yes, it's very close to 9 and 10. That shows you how reactive potassium is. Highly reactive. Very, very reactive. Very close to the central points, 9 and 10. So, the correct option is not D, magnesium. The correct option is not C, calcium. The correct option is not B, sodium. But all for your correct option, which is A, potassium. Correct. Potassium is the most reactive. Thank you so much for taking this lecture, and I hope you enjoyed the lecture and you must have gotten one or two things that will be beneficial to you in your Jamb UTME. Congratulations on your newly earned 1 mark in your Jamb UTME 2026, and do not forget to subscribe and follow for more at Nkwado Augustine across all social media platforms. Hope you made notes for your subsequent revision. After this lecture, revise your notes and practice, and see yourself solve this question like a machine in the UTME examination hall. If you have any topic or question for suggestion, do well to drop it on the comment section. I am going to do justice to your questions and knowledge gap as soon as I come across them. At this point, I'm out.